Okay, Assalamualaikum and hi. My name is Muhammad Aziz Azim. Today we want to present our group project and we use the dataset chess. And okay, this is our group member. Number one is me, Muhammad Aziz Azim Zamri. Number two is Muhammad Syarul Ilham bin Muhammad Najib. Number three is Muhammad Aziz Aiman bin Muhammad Zamzuri. Number four is Muhammad Ashraf bin Zulfahmi. And lastly, number five is Muhammad Nur Syafiq bin Shahruddin.
Okay, the first part is introduction. Okay, decision support system (DSS) leverage machine learning (ML) to turn complex data into actionable insights, enhancing decision making in fields like healthcare, business, and gaming. This project develops a DSS prototype using Weka's J48 decision tree algorithm on the kill chess dataset, which is key rook versus king pawn, to predict game outcomes based on board configurations. The J48 algorithm, known for its interpretability, analyzes key chess features like piece positions and mobility, generating clear rules for strategic moves. Both in Weka for its user-friendly tools, this DSS demonstrates how ML can provide real-time, explainable predictions, bridging data analysis, and practical decision-making in chess while setting the stage for future advanced ML applications in gaming and beyond. The next part is literature review. Machine learning (ML) improves decision support systems (DSS) by providing accurate and interpretable predictions. The J48 decision tree is widely used in healthcare and gaming, like chess, for clear decision making. Recent advances in cloud computing enable real-time DSS for applications like finance and strategy games. Future DSS may combine decision trees with neural networks for better performance while maintaining explainability.
Okay, next I will explain about the methodology and framework that we are using in this project. And firstly, the project developed a decision support system to predict chess game outcomes. And it used the J48 decision tree algorithm within the Weka platform, and the Simon model framework guide the process through three phases, that is intelligent, design and choice. For the intelligent is about problem definition and data collection, and for design, model building using J48, and for the choice, model evaluation and validation. And the KEEL chess dataset is used for classification tasks, and the project shows how machine learning can turn complex chess data into useful insight for this decision making. Okay, for the intelligent phases, this sets the foundation by defining the problem, gathering data, and performing initial analysis. The goal is to predict outcomes in king rook vs king pawn, chess endgame using board configuration, and the kill chess dataset is used containing features like piece position, blowy, and mobility metric RK web. And the dataset is loaded and exported using Weka Web Explorer tools, and the data is converted into ARFF format for Weka compatibility. And Weka tools like classify, alter, and select attribute help check data quality, missing values, and attribute consistency. Next, preliminary analysis shows that blowy is a strong feature for classification, and the dataset contains around 19,000 instances, indicating good data volume. And filters and closure are applied to clean and refine the dataset. By the end of these phases, the data is clean, consistent, and ready for model development. Okay, next we will move to design phase, and this phase is focused on building and testing solution using the J48 processing tools. And Weka 386 is used for its user-friendly interface and powerful data processing tools. And why we choose J48 is chosen for its balance of interpretability and performance with both categorical and numerical data, and the model is trained with default setting using a confidence factor of 0.25 for pruning and to reduce overfitting. And J48 also generate decision rules that connect chessboard features to predict outcomes, and the alternative classifier like random forest and red tree are tested for comparison. And visualization tools, that is Weka, Trigrapher and Draw.io, are used to display the decision tree structure, and these visuals help user understand how the model makes prediction, and by the end of these phases, a working DSS prototype is created that offer real-time, rule-based prediction. For the next phase is choice phase, and this choice phase is evaluate the DSS prototype to ensure it perform well and is ready for use. And a tenfold cross-validation method is used to test the model generalization and avoid overfitting. And there is several key performance metrics are assessed. There is accuracy, that's measure how many predictions are correct. And for the second one is precision and recall, that's evaluate how well the model identifies correct outcomes. And for the third one is F measure, that balance precision and recall useful for multi-class tasks. And for the fourth one is kappa statistic, that is measure prediction agreement beyond chance. And the last one is MAE and RMSE, that measure the size of prediction errors. And the result shows that J48 perform with high accuracy and strong interpretability. And this model is clear that decision rules and solid performance make it well suited for real-world DSS application.
Okay, for the next part, I will present the analysis and design. For this project, we use several tools to help with the decision making, including decision trees, flowchart, influence diagram, AHP, and production rules. We use a chess endgame dataset that shows the position of the white king, white rook, and black king, along with the result, either win or not. So, the data that we got is converted to ARFF format, so it can be used in Weka. The In this project, Weka is used to build models like decision tree, production rules, that helps to predict the best move. While Draw.io is used to design the flowchart and AHP diagram. Both of the flowchart and AHP diagram is used to show the decision step clearly. By using these tools, we can understand how decision are made in chess and improve the strategy. uh, for for decision tree for this project, we use the J48 decision tree algorithm in Weka to classify the chess dataset. The model is built using the position of the white king, white rook, and black king. It also generates a clear classification rules that help predict whether a position will lead to a win or not in a chess game. So, the decision tree also show useful details like the number of leaves and the size of the tree, which reflect how complex the decision process is. So the decision tree splits the data based on piece position. Each branch represents a decision point, and each path leads to a prediction, either win or not, either win or non-win. This makes it easier to understand how different chessboard setups affect the outcome. Overall, the decision tree helps make accurate and easy to follow decision based on chess piece position. Next, as you can see, this is our decision tree that we got from Weka. After decision tree, we also use decision table. Okay, the decision table is a classifier in Weka that was used to test the chess dataset. It was evaluated using the tenfold cross validation on 3,196 instances. The model correctly classified 97.22% of the data, with only 2.78% misclassified. The kappa statistics of 0.9442 shows strong agreement between the predicted and actual outcome. The model also performed well with a mean absolute error of 0.079. and a root mean square error of 0.1623, indicating a high accuracy. So the table 1 which shows the full configuration and evaluation result for this model. This is the table, decision table. The rule, the rule is R1 and R2. For the R1, the condition is feature 1, 6, 10, 14, 15, 21, 23, 30, 33, 37 that satisfy the best fit subset logic. And the classification for this condition is win. For the next rule, which is R2, the condition is if condition does not satisfy majority rules, the classification will be no win.
Okay, my name is Muhammad Azizal Azim, and now I want to talk about our flowchart. The flowchart visually represent the decision-making process for classifying chess endgame outcomes based on the position of the white king, white rook, and black king. Starting from key piece position, the chart guides through several decision points that lead to a final classification of the game. Result as either a win or non-win. It provides a clear and structured path to understand how positional factor affect the outcome. And I will show the flowchart, and the step in the process are as a follow. As you can see, there is 14 step. Okay. For the first step is start the classification process. Number two is check if white king column tile index is true. For and it will go to the number 3 and 4. If true, go to step 3, and B if false, go to step 5. Check if sketch true, and now we will go to number 6 and 7. For if true, classify the outcome as 1, and B is if false, classify the outcome as no win. Number 8 is end the classification process. Number 9 is check if white king overall location is true. If true, classify the outcome as 1. If false, go to step 6. Check if rook x axis move square is true. If true, classify the outcome as 1. B if false, classify the outcome as non-win. And the classification process. Okay, as you can see here, this is our flowchart.
Okay, this is our influence diagram of a Bayesian network generated using Weka BayesNet classifier. At the top at the top center, the node label class serves as the target variable, while all other attribute node like BBIK, BKNWY, Bicona, and another attribute node. This is our analytical hierarchy process model developed for classify chess game outcome, where the main goal is to determine whether a game was won or not won. This, this classification decision is guided by three criteria: WKCTI, WKNA8, and WKPOS. These features likely represent key position or strategic aspect in the chess game that influence the outcome. The alternative at the top, won and no won, represent the two possible classification for the game result. Okay, this is a production rule, and we have three men. Rule one: if remake F and bug D, then classify as no win. 7 for 3.0 instances. And rule two: if Steam is C is F, and remake is D, then classify as 1. 5 8 4.0 instances. And rule three: if reg is T and 0 is T and Mowi is T, then classified as Norwin 255.0 instances. Okay, the next part is result. The J48 decision tree model was evaluated using 10-fold crossover validation on the chess dataset. Key performance metrics include: the first one is accuracy, the second one is precision, the third one is recall, and the fourth one is F1 score. The confusion matrix shows strong classification performance for all chess species. These results demonstrate the J48 algorithm's effectiveness for this task. Okay, the next part is summary performance. The model performed exceptionally well in cross-validation, achieving 99.5% 44% accuracy with only 0.55% misclassifications. The kappa score of 10.9687 indicates near perfect agreement between predictions and actual results. Errors were minimal and relative errors were low. Overall, the model demonstrates strong predictive power. Okay. The next one is precision, recall, and F measure. The model achieves excellent performance with high precision, recall, and F1 score for both classes. False positives are minimal and the ROC area and the RC area confirm strong discriminative power. Weighted average indicate balanced class performance, making the model highly reliable for predictions. Okay, the last one is precision recall confusion matrix. The model demonstrates outstanding classification performance, correctly identifying 160 1000 1,662 won cases and 150,016 no-win cases while making only 18 total errors. It achieves 99.6% precision for the one class, meaning nearly all positive predictions are correct, and 99.3% recall, showing excellent coverage of actual positive cases. The no-win class performs similarly well with 99.3% precision and 99.5% recall, confirming balanced accuracy across both categories. With just 7 false positives and 11 false negatives, the model maintains remarkably low error rates while delivering consistently reliable predictions for both classes. These results confirm the model's strong ability to distinguish between the two groups with near perfect accuracy.
For the conclusion, in this project, we built a prototype decision support system that we predict the outcome of chess endgame using Weka J48 Decision Tree algorithm. The system achieves high accuracy of 99.44%, showing that decision trees are effective for strategic decision making like in chess. We use key features such as piece, position, and movement to train the model. The decision tree gave clear and understandable rules, which is useful for systems that need transparency. Weka 3.8.9 made it easy to train models, view trees, and analyze results. For future improvement, we suggest trying advanced model like neural network for expanding to more complex game or world problem. In conclusion, our DSS prove that machine learning, especially decision trees, can support smart, reliable decision in various fields. Thank you.